some special functions in fractional calculus. So I see lot of crowd which is new to this subject. So this some few remarks on fractional calculus. So as everybody knows that Leibniz introduced this symbol of nth derivative, and he reported this in a letter to L. Opitha with the implicit assumption that this small n is a natural number. And in a letter dated 30th of September 1695, Opitha asked, what does it mean when n is half? So since then, so the development of fractional calculus began in the similar era when calculus was being developed. And historical perspective, if I want to give, it was Leonhard Euler who realized that if one wants to extend this notion of order of derivatives to arbitrary real numbers, then one has to generalize the concept of factorial. Because if you see, a simple motivation is if x to the power n, and if you want to take mth derivative, you have n factorial divided by n minus m factorial into x raised to n, a simple formula. Now if m is not an integer, and say suppose some positive real number, then it would, this n minus m would be some number which is not natural number. So what would be its factorial? So it was Leonhard Euler, the great mathematician, who introduced gamma function as integral in convergent integral converging for values x for x greater than minus 1. And this integral is a generalization. It produces x factorial when x is a natural number. So this was one special function which plays pivotal role in the development of fractional calculus. Now with this, you can just see n factorial is gamma n plus 1 and n minus m factorial is gamma. And the interesting thing is this factor, gamma n minus m plus 1, is defined even if the argument is non-integer. And when you put n is 1 and m is half, and this is a kind of brief answer for one simple function, what you expect as a half-ordered derivative. Then Fourier generalized this in 1822. He introduced alpha-th derivative if you want to take. When alpha is any real number, he introduced this phase to this cos. So when alpha is 1, it is cos of some theta plus pi by 2, which is in terms of sine theta. So this is a one generalization. So like that, there were generalizations of small kind of contributions, you should say, incremental development. And fractional derivative of a function, nth order derivative, when I take it will be n to the power n. When I take alpha, you expect a to the power alpha. And also there are some inconsistencies also. So when Liouville introduced this formula, soon after that it was pointed out that there is an inconsistency, which was then resolved. And for that, Liouville's definition includes integration from minus infinity to x. And we will come to subsequently Riemann's definition, which is on a finite interval. And what after these two developments, what you find today, Riemann-Liouville derivative, which is on a finite interval. So let me just motivate what is a differ integral, which was further developed by Grunwald and Letnikov. So differ integral is, so ordinary derivative, first order derivative is this limit fx minus h by h. Second order derivative is second order difference divided by h square. In general, for nth order derivative, you will have this summation. So you can see plus minus sign alternately coming, and these coefficients are binomial coefficients. N choose j minus. So if you consider this divided by h to the power n, You can prove it is a simple exercise to show that this is your usual nth order derivative, where n is a natural number. Now, when one wants to modify it, for example, one variable calculus, you have a concept of derivative. When you go to multivariable calculus, the concept of derivative is drastically different. That generalization is non-trivial. So then you define the, if you consider function from f from Rn to Rm, then you have a matrix as your derivative. So this is a where that talent or genius comes, who generalizes it in a very meaningful way. And here I just want you to observe how we will jump it, so that for minus n also this limit will make sense. So for that, first note that when j is from 0 to n, I can also say j is from 0 to infinity, because when j exceeds n, it is 0. So I can equally write it as 0. Now this infinity plays very important role in fractional calculus. So consider a base point and define x greater than a. So consider interval a to x and divide that interval into capital N number of partitions. So d of minus n, then you substitute here. So when n goes to minus n, this is the way you modify your n choose j symbol, and this is the way you define minus n choose j is this minus n minus n minus 1 up to minus n minus j plus 1 j factorial. J is a natural number, and then substitute. So this is the way, this is a genius who generalizes this, and that definition makes sense because if you, this is a exercise and you can refer to standard book uh, on fractional calculus, that this limit given in 2 is nothing but the integral given in 3. So this is the beauty. So when you replace n by minus n, you get a to x, x minus tau n to the power n minus 1 upon n minus 1 factorial f tau d tau, which is again a simple exercise to show that it is a repeated integral. Hello, am I audible? There is no problem, I suppose.
Yes, ma'am. Yes, ma'am. Yes,
Ah,
you are audible, ma'am.
yeah.
No issue.
So it is a simple exercise to show that this convolution, as you say, is equivalent to this n-fold repeated integral. Now Grunwald-Letnikov differ integral is nothing but you just now replace this n or minus n by arbitrary number q. It could be positive, negative, and now you define q choose j as q minus 1, q minus j plus 1 upon j factorial, and simply replace this. So first it was n, then minus n. N was the nth order derivative, minus n gave you n-fold integral. Now you just replace it and keep it as q with this definition. And interestingly, it is in Oldham and Spanier, the classical book, where this development of recent times has popped up, and it is basically credit goes to this classical book which created impetus. Time and time again you have to visit and revisit that subject. So this is a classic book. Everybody should have a copy who is interested in fractional calculus, and this is also not a very costly book. That this integral phi, this limit, is nothing but this Riemann sum given in 6. So when q is negative, you can show that it is this integral a to x x. So when f has some decent conditions, such as say f prime is integrable and or f is continuous. So I'm not going to those details here, because there is lot of analysis comes into play, which I am keeping aside. I'm just trying to motivate these young students about for the fractional calculus and how these special functions are coming up in this area. So when q is negative, you can show that this integral 5 takes this form, integral representation, which is our familiar definition of Riemann-Liouville fractional integral. And when q is positive, so it will lie between some two numbers, n minus 1 and n, then you can show that this limit, so these are proofs are actually given in Oldham and Spanier, and very simple. I mean, even a person or student who has done BSc mathematics should be able to follow that. This is not a very advanced or very abstract mathematics. So this is a generalization that phi u is equivalent to 7, and this is what is popularly used. So many papers are written. This is a Riemann-Liouville fractional derivative. So now you can just see that they are little complicated. So it took longer for this subject to develop, unlike fractional calculus. Unlike traditional calculus. In traditional calculus, what is happening is n choose j when n is positive. It becomes a finite sum. You see, this is the advantage. And here there are infinities. So composition rules, if you see, so this is the way we see, this is a fractional derivative, and for q negative, this is derivative. Now this I will denote by iq because it is integral. So d of q when q is negative is iq. So dq acting on iq is fx. So that means this is left inverse. dq is left inverse. When I operate this dq from the right, I get fx plus this initial conditions. So this is a normal thing. Even in nth order derivative, you will have such a polynomial coming there. So this is a very generalization in tune with ordinary calculus. Now comes the Leibniz rule. Leibniz rule is, you can see the infinities come here. Because alpha choose k, when alpha is not an integer, this becomes infinite. When alpha is an integer, this infinite series is truncated. Because when alpha is n, when k exceeds n, it is all 0. And that is the beauty of traditional calculus, that you have compact expressions. And in fractional calculus, you have complicated expressions, one should say. And that is, but now you see the researchers are finding applicability of this. Very powerful applications are upcoming. So these derivatives are popular. Now Laplace transform one can take because it is a convolution and it is given. So these quantities and these expressions are useful when you solve differential equations involving fractional order derivatives. Only limitation is that these symbols like this evaluated at t equal to 0. So one drawback of fractional calculus is that its physical interpretations are not there. So not there in the sense as simple as, so ordinary calculus, the physical interpretation is in simple terms: rate of change of curve, slope of that tangent. In such simple terms, you don't have applications here, but one can come to the application part later on. Now, some remarks are in order. Now, Riemann-Liouville derivative of a constant function is given here, which is non-zero. This is one of the unique feature of Riemann-Liouville derivative. Another thing is, what is the use of all these extensions? So simple example I have given here, that consider this function. It is 1 minus y and y minus 1. So it is a like fx equal to mod x kind of graph, only shifted at t equal to 1. So at t equal to 1, the function is non-differentiable. So its derivative doesn't exist at t equal to 1. Or rather, I should say here at y equal to 1. It should not be t equal to 1. It is f of y. So sorry, it should be y equal to 1. Now here, if I consider its Riemann-Liouville derivative, so I take this function, it's a simple function, put in those definitions, and I get these expressions given in 12. So Riemann-Liouville derivative of order beta exists, where beta is between 0 and 1. So the Riemann-Liouville derivative of order beta of this function exists at y equal to 1. Sorry about this, t equal to y equal to 1. Although the function is non-differentiable there. So Riemann-Liouville derivative captures lower order differentiability. It is not differentiable at order 1, but it is differentiable of order 0.99, for example, and all lower orders. So this is the beauty, and it tackles some such differential equations. Now a generalization of exponential function was suggested. So just as the role played by exponential function in ordinary differential equations is taken up by Metagrapher function introduced by Swedish mathematician Metagrapher, and its generalization by introduced by Wieman in 1905 is given in 13. So when beta is equal to 1, you have expression given in 14, z to the power k upon gamma alpha k plus 1, which is a generalization of exponential function. When alpha is 1, this is gamma k plus 1, which is k factorial. So this is summation k going from 0 to infinity z to the power k upon k factorial, which is exponential of z. So it is a generalization. And this is a alpha comma beta is a 2-parameter generalization. Now there are many more. So one will see firstly that the convergence, the series is convergent. With these expressions I have given you, 13 and 14, they are convergent uniformly and absolutely for every z. And you can see it is a direct generalization of exponential function. Relation to Metagrapher function with special functions, I have listed a few functions here. So E1 is nothing but E1 comma 1, which is nothing but e to the power z. E1 comma 2 is e to the power z minus 1 by z. E2 comma 2z. So you can check this list. E2z cos square root z. E2 minus z square. E2z is cos square root z. E2 minus z square. Then E half z to the power half is this error function. So which is another special function. Now there are some properties that 2-parameter Metagrapher functions are entire functions, except for E1 comma 1. All other Metagrapher functions have infinite zeros. So this is yet interesting factor, that exponential function has no zeros usual, but its generalization Metagrapher function has infinite zeros in complex plane. So this fact has implications in fractional calculus or in fractional differential equation. E alpha minus x is completely monotonic function. Then I have listed a few properties which will be having very important applications. Say E alpha x, when alpha lies between 0 and 1, and when x is a real number, it has no real zeros, and is so there are no zeros. So like exponential function, E alpha x, when alpha lies between 0 and 1, it has no zeros. And this fact we will come to see has applications, very important and far-reaching consequences. Another interesting property of Metagrapher function is does not satisfy semigroup property. That means just as exponential function has e to the power a plus b is e to the power a into e to the power b. Simple. But e alpha comma beta a plus b is not equal to this. So that means it doesn't satisfy semigroup property. This is the expression for Laplace transform, and 20 we have given what is the fractional integral of these arguments. You know, when you come for solving fractional differential equations, all these expressions come handy. So I have just enlisted to give you some overview of these special functions, their properties, which every student should sit down and revise and write down themselves. Now here we will just check some simple observation that if you consider the function e alpha lambda t to the power alpha, where lambda is a real number, and consider alpha order derivative. When I don't write anything down, it means from 0 to alpha. The base point is at 0. Mind you, fractional order derivative is a non-local object. It requires a base point. And without loss of generality, most of the times you take that base point at 0, and the convention is that when you have a 0 as a base point, you simply don't write anything. And that is the convention followed all through the lecture. Now, alpha lying between m minus 1 and m. So, case 1, when lambda is 0. When lambda is 0, what is you have? E alpha 0. Lambda is 0 means E alpha 0. E alpha 0 is 1, and this is 0. Now, when lambda is not 0, when you do this term by term, so this is an infinite series, and this is d alpha, and then you do interchange. You take d alpha inside and calculate this. So, this is, now note here that this d alpha when I am writing, so this is a, you can see the difference. This is two lines are here, and this is one line. Now this d alpha, what we are doing is, this is a traditionally done, that you subtract out the value at the origin, or what we say is you interchange and define what is called as the Caputo derivative. So here the definition is little twisted. So in fractional calculus, that is another limitation or hurdle, that you have many definitions, inequivalent definitions of fractional order derivatives. So that is why your d alpha 1 is 0 here. So this is the artifact, that you modify the definitions, and which was done by Professor Caputo. What he did, so here, for example, Metagrapher, I'm sorry, this is the definition given by Riemann-Liouville, where you first take this integral, fractional integral, followed by nth order derivative. In Caputo's definition, this is interchange. You first take nth order derivative, followed by fractional integral. And this Caputo derivative plays important role from the viewpoints of application, from viewpoint of applications, because in that case, fractional order derivative of a constant is 0, and that is a desirable property. And then if you apply d alpha of f of t, what you get by this rearrangement of terms which is given here is lambda e alpha lambda t alpha. So in nutshell, if I take d alpha of f of t, lambda comes out and you again get f of t, something like eigenvalue problem. So that is where you can see it's a beautiful thing that comes up. Now, why exponentiation is important? So let us come to ordinary dynamics. So let us recall. So this is exponentiation on matrix, which you do in linear dynamical systems. So first we define convergence of a sequence of matrices. So consider a sequence of matrices AM. These are n cross n real matrices. They said to converge to a matrix A if there exists capital N such that AM minus A, their difference, and you consider the operator norm. You know, matrix is operator, and you can have a matrix operator norm. So a little bit of functional analysis is required. So in that norm is less than epsilon, then you say the sequence of matrices, that sequence converges to the matrix A. So in the same line, you define now e to the power A, where A is a matrix. And what is that matrix? It is summation k going from 0 to infinity, A to the power k factorial k. So what we are now generalizing? We are generalizing exponentiation to matrix arguments. So here this is this sequence, this series is a limit of this sequence Sn. Sn is summation up to nth term, and then you take the limit. And here you have defined the limit and convergence of limit for a sequence of matrices. So with this, I think those who are new to or undergraduate studies or doing, so if they don't know exponentiation of matrix, it is a very important uh, kind of property or important concept, and it is defined here. Now, e to the power 0, if I consider 0 means 0 matrix, then it is identity. And another thing is, if A and B are n cross n matrices which commute, AB equal to BA, then e to the power A plus B is e to the power A. Note here that this capital A, capital B are matrices. And this property holds good when they commute. Now when A is a matrix, e to the power A inverse is nothing but e to the power minus A. And fourth property is exponentiation of P inverse AP. So you know this is a similarity transformation on the matrix is nothing but P inverse e to the power A P. And this is P is a invertible matrix. So when you have A and B similar matrices, you can do this. And what do you get? E to the power A is e to the power P B P inverse, which is nothing but P e to the power B P inverse, this product. So this is a finite product. And this is exponentiation is an infinite series. Now, if A is a diagonal matrix, then it is a simple thing. That e to the power A is nothing but you have a matrix with these diagonal entries. And with this, you can relate the properties of exponentiation matrix with the properties of its eigenvalues. So matrix exponentiation comes in this solving such a system of linear equations. So dx by dt is ax, where x is now in Rn, it is a vector, x1, x2, xn, and x1 dot, x2 dot, xn dot is a column, A is n by n matrix, and this x is x1, x2, xn. So this is a linear system with x0 is x0, and x0 also has these n components. So it has a unique solution in terms of e to the power ta x0. So here comes the exponentiation of this matrix. So this is a very traditional and simple kind of topic. Now when you generalize this, so you have to generalize firstly Metagrapher function for matrix arguments. So this is defined on the similar lines here. A is a matrix, and instead of factorial now you have gamma alpha k plus beta, and you can show that this is convergent. That is important, that you can write any series, but it makes sense only when it is shown to be convergent. So here is a simple proof that E alpha comma beta with matrix argument, this norm is equal to this by properties of norm. It is less equal this norm x, and x is some number, so norm x is a real number, which implies that E alpha comma beta operator norm is bounded, and that is why once you have this bounding, these functions are well defined, and Metagrapher function of matrix arguments is well defined for all A. And here are certain properties which I have enlisted, that E alpha comma beta evaluated at 0 is this quantity E 1 comma 1 A is nothing but exponentiation of A, where A is a real matrix in cross in real matrix. If A is a diagonal matrix, then E alpha comma beta A is nothing but a matrix with these diagonal entries. Now E alpha comma beta lambda 1. So this is a scalar. So this will be a number. So these are the diagonal entries. So similarly, so why I'm giving you these details, because they come handy when you are solving systems of equations having fractional ordered derivatives. And E alpha beta P inverse AP, you can easily see that this is P inverse AP to the power K upon gamma alpha K plus beta, which is, you can show, is P inverse A to the power KP, which is nothing but finally P inverse E alpha comma AP. So this shows that this exponentiation, when you do, the properties of the matrix, exponentiated matrix, are related to the eigenvalues of that matrix. And exponentiation or Metagrapher exponentiation, you can say, of that eigenvalue. Another property is, if matrix A has operator norm less than 1, then one identity minus A is invertible, and summation A to the power K going from 0 to infinity, is 1 upon identity minus A. So this will remind you of that simple geometric series when you have mod x less than 1, then summation x to the power k is 1 upon 1 minus x when mod x less than 1. So it carries forward even to matrices. Now Laplace transform of Metagrapher function with matrix argument is given in this, where now here A is a matrix and this is the operator norm A, and this Laplace transform is given in expression 30, and which comes handy when you solve such systems. Now let us come to the application of all the jargon that we have developed just now. And Metagrapher function with matrix argument is important, since the solutions of fractional order dynamical systems are can be expressed in terms of them. So here is this result which we have proved. So this one is our paper, analysis of system of fractional differential equation, published in 2004. So there is a variety of papers we have published in this thing. So to that we can come later. Sorry. So here we have shown that if A is an n by n matrix, and consider this initial value problem. So instead of first order derivative x1 dot, x2 dot, xn dot, that column vector, we consider d alpha means fractional order derivative of order alpha, where alpha lies between 0 and 1. Then it has unique solution E alpha comma 1 T alpha A. So you can see this exponentiation is nicely replaced by Metagrapher. So Metagrapher function comes very often, or most of the times, rather all the time, you can say. So this is the beauty, and it comes in its generalizations forms. So for example, consider the non-linear differential equation given in 32. So with my students Sangeeta Chaudhary, this is exercise we calculated. So this is a equation, non-linear equation, and if we put the boundary condition u0 is u of t, then it is equivalent to the fractional integral equation. 32 is equivalent to 33, where g t comma s is the called as the Green's function. So this existed even if in the ordinary case when alpha 1 is 1. Now its generalized form one can show that this is the expression. You can see it is little complicated, but the role played by the Metagrapher function is very clear. So here the E alpha comma 1 comes, and here E alpha comma 1 alpha, alpha 1 comma alpha 1 and all that. Now further what we considered is, here we can replace this by a string, the D alpha 1 plus a kind of combination, linear combination, D alpha 2 and all that. Lying alpha lambda is lying between 0 and 1. And you get still big expression. I mean, the expression runs in pages. But beauty is you get analytic expressions in terms of Metagrapher functions. So that is where the role of this special function comes in. So this is another generalization introduced by Hadid and Luchko, multi-parameter Metagrapher function. So arguments are also z1, z2, zn, and these parameters are also alpha 1, alpha 2, alpha n, comma beta. And this is the definition given in 36, where now binomial coefficients are replaced by multinomial coefficients given in 37. So k comma L1 L2 Ln is nothing but k factorial upon L1 factorial L2 factorial and so on. And with this multinomial generalization, with my student Hussein Jafri, we introduced a Metagrapher function for matrix arguments, a generalization. So what we introduced was these A1, A2, An are matrices, and alpha 1, alpha 2, alpha n, these are the orders, comma beta, and this is the generalization. So here this is firstly single AI1, then AI1, AI2, I1 going from 1 to n, all these products. And factorials are replaced by this alpha I1, alpha I2. And like that, nth order term and so up to infinity. So you might imagine the complexity of the definition, but what is the use? And interestingly, we could show that this is a solution. I mean, if I consider now system of equations here, where alpha bar is nothing but alpha 1, alpha 2, alpha n, y bar is y1, y2, yn. So you can say that in this system, here whatever we consider, everywhere you have one alpha, alpha, alpha. What I am now doing is I am changing and taking derivative of x1 with alpha 1 order, derivative of x2 alpha 2, derivative of xn alpha n order. I'm a little bit complication, and the solution of that is in terms of this series, where I have alpha 1 alpha. So very interesting kind of observation, that for this system, linear system, because A is a real matrix, is in terms of this E alpha 1, alpha 2, alpha n, comma n. When now matrix arguments are x to the power alpha 1, A1. What is A1? A1 is nothing but take this A, keep the row as it is, first row, all other 0. A2 is take A, keep the second row, put all zeros everywhere. That is the way you have these arguments, and you can show that this matrix representation is an analytic solution of this system of equations. So one can see the power of generalization, and how these special functions are generalized, and how they are generalized meaningfully. They are coming up as solutions of such interesting systems of equations. Now with this, I think I have motivated you, I hope, enough. So there is lot of work in this area has been done by our group, by other groups. Now for how do we solve such things? This is another topic of research. So there are methods. Adomian decomposition method is one such method. While this was done, some Adomian computations are complicated. So we developed our new iterative method. And how we observed this, so many interesting exact solutions we could guess because of the Mathematica. So don't undermine the applications or utilization of softwares like Mathematica, MATLAB, because these derivatives, as they are non-local, they involve lot of computation, computational time. If you ask the computer to do ordinary derivative, it is a simple thing, finitely many terms. And as I pointed out, when you do fractional calculus, you infinities come into play. So your integration, and it doesn't obey that composition, semi-group property. So all the time you have to integrate from the base point. So in nutshell, when you do fractional calculus on computers, the computational power you require tremendous computational power. So to curtail down that, one has to develop smart and efficient methods. So here is our work where we have developed these predictor corrector methods for solving various equations. Now various analysis theorems are used. So there are twofold activity we have done. One is numerical work, another is computational numerical computations, other is analytic approach. So my point is that it is all intermingled. I mean, research, you never know that where you will end up. So while doing numerical work, some interesting analytical methods are found and interesting analytical solutions we could observe, and so on. So this is where now I have given this little biography, bibliography, where now some important papers I have enlisted. There are another methods also, such as homotopy perturbation techniques, variational iteration techniques, Sumudu transform methods, and all of them. And then with my students, so Sangeeta Chaudhary and others collaborators, we have developed invariant subspace methods and so on. So there is a lot of activity going on in this field, and those who are newcomers can find interesting problems to work on. So with these words, I take your leave, and you are free to ask any questions if you have. Thank you so much. I once again thank Dr. Dilip Kumar and authorities of the mathematics department, Kerala University, for taking this initiative. I'm sure that students attending this will find this lecture series and seminars and conferences very useful done under this scheme. So thank you.